Mm,
Hello, everyone. Oh.
Hello.
Okay. Uh, until more show up from other students, I will go over what we have covered so far. For this topic, we have started by trying the generic statement, and we used it in this program. I believe you all did it. And this was the test bench for it. It was a simple counter. And we saw how we may shift very easily from 8-bit to 16-bit. Then we used multiple generics. So we had here two generics, bits and terminal count. And we tested together this terminal count. It was 255, and we changed it to 100, and how it did change the output. And we used the VHDL generate statement. And we saw how generate statement would make the programming is very easy, because I am calling the D flip-flop module, or the small program of D flip-flop. I'm calling it all the time. I called it here about 7 times for 8-bit in one loop statement, instead of how we did it in the past, writing it 7 times or 8 times. Here I have, this is the least significant bit, and those are the next 7 bits. And regarding the homework, if you look at 5B, you are going to see that those 3 programs that we did are repeated here in 5B. So we are ready to go with 5B. You have completed 5B because we did it in our last class. So 5B is ready. Now we go back to our lecture. And we are starting with switch bouncing. Switch bouncing. What do we mean by switch bouncing? The switch has internal spring. And this spring is moving from one position to the other. And when it reaches the final destination, due to the spring, it contacts, then disconnects momentarily, then go back and contact again. And that is happening here in this figure. You can see this oscillation. The switch is closed and it is bouncing between contact and no contact. This might be interpreted as 0101. Of course, I am moving from high level to low level. I need to stay in low level. Or if I'm going from low to high, I want to go to high, but not bouncing in between. So we are going to learn how we can avoid this or mitigate this problem by using this switch debouncer circuit. In this switch debouncer circuit, I start with, this is my input, and I have here 2 cascaded flip-flops. They are working at the same clock. Here I have what? The output of the first flip-flop is feeding the next flip-flop. And I am comparing the output of the first to the output of the second flip-flops. And in normal condition, the two outputs should be the same. If steady state, or sorry, if the output here is 0 and I'm getting 0 and the input is 0, 0, 0 transferred after 1 clock cycle. And at steady state, the two outputs Q0 and Q1 should be the same. The same as 0 or the same as 1. What will happen if they are different? If they are different, I am feeding XOR. XOR, how does it behave? XOR, it looks for the difference. If the two inputs of the XOR are different, I will get 1. If they are identical, I will get 0. So what I'm having here is a counter. If those two are identical 0 or identical 1, I will get output here to be 0. If different, due to bouncing, I will get 1. 1 would mean clear. The counter is not working. The counter is not working. So if I have difference between Q0 and Q1, I have a clear command. A clear command will be interpreted as 0. 0 output. The counter is reset to 0. What does it mean? It means I am not enabling my third flip-flop. My third flip-flop, it is not enabled. That means the output of Q2 that is feeding flip-flop 3 will not go to my final output. Okay, when will it go? If this enable is high. And when will this enable be high? If the counter operates and it reaches the terminal count. If I say my terminal count is 5, okay, 5. I have here high. When will I get S clear low? When I have S clear low 0, I will start counting. Otherwise, I will never start counting. So whenever I have those two, Q0 and Q1 identical, I have here output 0, S clear is not assertive, so I will start counting. When I reach the terminal count, I am enabling my D3 to go to Q3. So I have to have identical inputs from Q0 and Q1 to S clear to be 0, and I start counting. When I reach the terminal count, also, I have here 1 enabling flip-flop 3. Now, how do I select the terminal count of my counter, or how many bits do I need? If I use 1 bit, I will count just 1 clock cycle, 0, 1, done. So if I have 2, I will have 4 clock cycles. If I have 3, I can increase, but what is the limit? This depends on your switch bouncing. I want to maintain or make sure that the two signals are stable and identical. So I am selecting the counter, the number of bits of the counter, according to how long do I need the two signals to be stable and identical. In this slide, it says the period, that is P, time, and this time is normally 10 milliseconds to 300 milliseconds to 30 milliseconds. This is the time that would guarantee a stable operation of my switch with no bouncing. So I know this is T, and T equals here my time. It is T. This time I am saying 2 to the power n. N is the number of bits plus 2. Why do we say plus 2? Because I have the first and the second flip-flop. I need extra 2 clocks for those 2 flip-flops. And normally, those 2 clock cycles are nothing compared to 2 to the power n. So 2 to the power n over f, this should be equal to my P. F is the 1 cycle, 1 clock. 1 clock, it is 1 over f. 1 clock, T is 1 over f. So I am dividing this 2n by f. And here we have an example. If I have here 0.01, that is 10 milliseconds, and I need to get 50 million times 0.01, this will give you 500,000 clock cycles. This is the number of clock cycles I need. And to get to this, I need 19-bit counter, 19-bit counter to count up to 500,000. We are counting from 0 to 500,000, so I need a 19-bit counter. Of course, this is with 10 milliseconds. If I go 20 or 30 milliseconds, I would need more bits. But for now, this is my N. Hello, Eric.
Hello, sir. How you doing?
Just fine. Is it clear for you how this is working?
I think I'm starting to get a hang of it. Yeah, I was the counter. I was getting unstuck on how the counter and its output enables, but I think it's starting to make more sense now.
Okay. Let me ask about this XOR. What does it do?
It's comparing the outputs of your DFF1 and DFF2, so it will only go high if they are different.
And if they are high, what will happen to the counter?
The counter will clear.
Will clear, so the output here will be 0.
Correct.
And if the output here is 0, would this flip-flop 3 be enabled?
No, it's enabled below.
It is not enabled, so I will not get the output here.
Mm-hmm.
And this output, of course, if I get it is incorrect because those two are not identical. So I do not need this output. So it is good not to enable it.
Mhm.
And meanwhile, if I have 0, this counter is ready. It is enabled, but it is ready, but it is clear. So that's why I have here a bubble. That means it is asserted on low voltage. I am enabling this, making it ready to count, but it will not count because I have here. Now, if those two are identical, what will be the output of the XOR?
So it would be low if those two signals are identical.
So if it is low, that means no
That it's
clear,
gonna start counting.
no clear. And I have C out still 0. I am enabling the counting. So now I am counting 1, 2, 3, 4, 5, 6. During the time where I am counting, I have no output. Don't forget that. While I am counting, I have no output. And during that time, the output of flip-flop 1 and 2 are still the same.
Mhm.
If it ever differs while I am counting, I will get a clear. But if they are identical while I am counting, counter will keep on counting until it reaches the terminal count. What is the terminal count? It is as high as I can go with my n bits. I have n bits. It can enable me, as we saw for 10 milliseconds, it can go as high as 500,000. So when I reach 500,000, after 10 milliseconds, I reach the terminal count. When I reach the terminal count, what will happen? Flip-flop 3 is enabled. So I am getting my output. And meanwhile, I have here C out high. C out is high. And when I have this high, I am saying the counter is not enabled anymore. Done. I stop counting and I reach the terminal count and I got my output. If I have another input, that will clear my counter. Why it will clear? Because D1, Q1 and Q2 will not be the same. So I am clearing the counting and I am waiting until those are identical and I will start counting one more time. Clear?
I have a question.
Yes, sir.
Can you go back to where it looks like the signal is bouncing up and down? That
Yes, sir.
graph. So are we setting the timer for that long amount, or is like the first bounce? Is that timing gonna be? Are we tuning it for the first bounce, or are we tuning it?
No,
for
the 10 millisecond is from this point to here, and even a little bit further.
Okay, so we're just accounting for the variations in between that.
Yeah.
Okay.
And as I said, it depends on the switch. You may get a switch with very strong spring that may make many oscillations. So the spring itself that dictates 10 or 20 or 30 milliseconds, just to make sure it is quite stable. But for our applications and with our just simple switches, 10 milliseconds will be more than enough. Any more questions? This is the program that we'll be doing right now. In this program, what we are going to be doing, we are going to do the same switch debouncing. The same switch debouncing that we spoke about with the 3 flip-flops and the counter. Those are my elements. 3 flip-flops, counter, XOR, those are my elements. And we are gonna implement it in this program. As you can see, I'm using again generic statement and the counter size is 19. And this should give me, as the comment statement, 10.5 millisecond if I have a clock 50 megahertz. My port will include what? Clock, any button, and the result. So I have the clock and my push button or my switch and the result. This is my entity. My architecture, I have here this signal, internal wire, and this signal, internal wire, all of those signal, internal wires, I am using them. For flip-flops, I have 1 down to 0, 2 flip-flops, and I have counter set and counter out. This is my begin, and we know this counter set, it is an XOR, taking the output of the first 2 flip-flops. I have it in here, XOR, flip-flop 0 and flip-flop 1. This is XORed. My process switch relies on the clock. If I have a clock, then the button, whatever the status of the button, high or low, will go to flip-flop 0. And flip-flop 0 would feed flip-flop 1. If counter set is 1, then what will happen? Counter out will be 0. Else if counter, and I'm saying the counter out, counter size is 0, this is stable input, stable input. I increment the counter. I keep on incrementing the counter until I reach the terminal count. When I reach the terminal count, result, that is the third flip-flop, will be equal to flip-flop 1. And this is the program we need to do. Clear, Joseph? Is it clear, Joe?
Yeah, I got it. Can you post this on the announcements? Because I don't see this in the slideshow on our side.
I couldn't hear you well. Would you please repeat your comment?
Oh, could you post this code on the announcements? Because it's not on the PowerPoint.
Okay. Unfortunately, it is a picture. As you can see, it is a picture.
Okay,
So you have it on the PowerPoint, I believe. So you
No,
may
it's
get it
not.
from there.
I can't find it
Oh.
either. Would you mind just leaving the example up full
Uh,
screen so
yeah.
that we can work
No,
off?
no,
it?
you can see it on the PowerPoint, you mean?
Yeah, I'm not seeing it either.
Okay,
I'm on
so
It's
lecture
14 for
week
you.
5A, it's not there.
let me go with you to my PowerPoint and try to show it. This is lecture 5A.
Yeah, we're down to slide 13 or 14 and it's not there.
Okay, it's my bad. Okay. Will you please check it now? Do you all
Got it
have it,
now, thank you.
5A?
I got it now, thank you.
Okay, thank you, sir. Go ahead, please. I will stop sharing. Any one of you may share the screen. Hello, Brandon?
Hello.
Hello, sir. Have you read your mail?
Yeah, I did.
Sorry about that. It doesn't seem that I'm gonna be able to go to 5A this morning. Okay, sorry.
Okay, so you said that'll be next week then?
Yes.
Okay, thank you.
Because as you see, we are doing this debouncing, and as soon as we finish debouncing, if you look at the lab, it is all debouncing. So we're gonna work on the lab and
Okay, thank
postpone
you.
5A to next week. Sorry about that.
Hey, Dr. Mitchell, I have a quick question. I was just curious, what is the functional difference with this line that we have, the clock event and clock equals 1 versus the rising edge clock that we usually use?
I believe the same.
Okay,
Would you please, when you run this and it works, try the other one?
yeah, I can do that.
Okay, thank you, sir.
No problem. Is there any way to extend the range to 100?
You could just reduce the number of bits on the counter.
So I set it to as much time as I could put in the waveform, but you can't put the counter all the way up.
Oh, yes, because you are limited by how many microseconds. Yes, yes, I know that.
So we could set the value of the counter just to see
Yeah.
it. Off.
Okay. And this is with the same code,
Yeah.
not rising edge.
Oh, well, I forgot to extend this out.
Okay.
Let me see if that does anything.
No, I believe it won't.
Oh, yeah, no, this is the same code. I'm just extending my button press out to see how high the counter can get.
So we may, just for testing, can we reduce this 10 millisecond to 1 millisecond?
Yeah.
And in this case, you don't need that 19-bit counter, just for testing.
Sure, I'll go back and do that.
Okay. Make it even 5-bit counter.
So I did an 8-bit counter just to try
Okay,
that
very
out.
good. Yes, yes.
And you can see I added some oscillations in the button, and you can see that the counter's not counting.
Yes, yes, yes. That's
But
good.
whenever it reaches the maximum, the output enable doesn't seem to be working.
Yep.
So does that look right? Isn't out supposed to go high?
The output should match the input.
Right. Oh, okay. So I should put something out there then maybe.
Yeah.
Let me fix that. So you can see it's oscillating and then the button remains high. And then once the counter finishes counting, output of Q3 is high.
Excellent. Thank you. Perfect. You may have a cup of tea. We have about 10 minutes more. Then I'm gonna go to our lab. So everyone can start working on the lab. But for now, just wait for 1 or 2 more demonstrations of the same thing. Whoever is ready, he may share the screen. If you are ready, please share the screen.
Can you see mine?
Okay.
I put the counter at 5, like you said,
Yes.
and then I put a little spot here where it bounces. and
Okay.
It started over again. And then it's been result is solid until it goes down again, starts counting right there.
Very good.
Thanks.
Thank you, sir. Daniel?
Hello.
Hello, sir. Are you ready?
I'm still working on it.
Okay, take your time. No problem. No problem. Hello, Bart?
Yes, I'm still working on it too.
Take your time. No problem.
All right, I did mine with 5-bit.
Okay, go ahead, sir.
So right at the start, I had in a small part. Oh, how do I zoom on this? Oh, there we go. Where I had the button bounce,
Yeah.
so you could see. Sorry, the zooming is. Goes high, flip flop goes high, flip flop goes high. Although, oh, I'm gonna take a second to look at the code. I don't think this is right.
Take your time. No problem.
Okay, it's fine. I was just misunderstanding. So, we got a button. It doesn't stay the same. You can see it resets the counter. The counter also counts when they're both. I thought that was an issue, but turns out it's coded that way.
So it is counting while we have a difference?
No, it's counting when they're both 0
Okay,
or both 1, and I didn't.
okay. That's very good.
And then yeah. So next I'm gonna put in the rising clock, and then I'll see if there's any difference.
Please do. Yes, thank you.
For anybody else that's curious, I can't find a difference between the two if you use Rising Edge for your if.
Yes. How do they differ?
I couldn't find a difference in the
As I
waveform.
told you, they should be the same. But anyway, we verified it. Thank you.
So this is what I had gotten. I didn't count all the way up, but doesn't look like flip-flops are.
When you reach the terminal count, the output is the same as the input?
I guess I didn't reach the terminal count, did I?
In the code, switch your bits to 5 where it's 19. And then you can start seeing something.
Yes,
Oh,
yes,
yeah.
35. Yes, that's it. Right now.
Okay.
Wait until it finishes. Has it finished?
Yeah, I believe so.
Okay, just wait until it finishes.
Here it goes.
Okay, great. Would you please just, yes, I will share the screen and go over our homework, our lab, sorry. Please get ready with our lab 3A. In this lab, as you may see, we are going to use our board. And when we use our board, that means I need to see on your submission a video clip of whatever you are doing, because of course we are not going to use any of the test bench or the waveform. I'm going to just see how it is working on your board. So we are going to start by doing a switch debouncer, any one of the switches on the board, and it should feed one of the LEDs of the board also. And we are going to use the up-down counter and reset. So I have a switch for count up if high, count down if low, and another switch for synchronous reset. Again, those will implement debouncing. And this first part 2 without debouncing, and part 3, this will implement the debouncing switch. So I'll try it first without debouncing, then part 3 will be using the debouncing on all of our switches. Any questions about this one? Any questions?
We're just not doing the part 4 and 5.
This is, oh yeah, sorry. Simulate your design. This you can, as I said, you can simulate it with test bench. You can simulate it with the wave4, whatever you like. That's it. Okay.
So we're using the board to do this, not the waveform.
We are gonna use one part for the switch debounce. This just the board. For
Okay.
up-down counter, we are going to use it twice. One with wave4 and the other one with the switch debounce. That's gonna be real time. So you are gonna be doing a video clip for the first and the third part.
Okay.
Whoever finish with the debounce, you may start working on the lab. And that is going to be all for this afternoon. For this afternoon, we have just the lab to do. And if you are done, you may leave. And next week, we are going to go to 5B, homework 5B.
Okay, thanks.
Thank you, sir. If you want to share the screen and show your debounce, you are welcome. If you want to go ahead and work on the lab directly, you are welcome, whatever you like. If you feel comfortable with it, you may leave, whatever you like. I am available for you.
Talk to you later. Bye-bye.
I do appreciate it.
All right.